Okay, so welcome everyone to this FAIRmat tutorial on molecular dynamics simulations. Just to remind you, you can get all the materials that we're going to go through on the webpage that Lucia just posted in the chat. And I'll give you more instructions as once we start the guided tutorial part. Also to remind you, the times that are the sort of schedule is we're going to keep relatively flexible. So we put estimates on the webpage, but we may adjust these depending on how fast different sections go. So we're going to start with Luca giving an overview of some of the FAIRmat and NOMAD basics. And then after that, we'll start with the guided tutorials. Please go ahead, Luca.
Okay, so you can hear me? Good.
Yes.
So welcome everybody. Thanks, Joe, for the introduction. What I would like to do now is to give a brief introduction to NOMAD and FAIRmat. Today's tutorial number 7 of a series in FAIRmat. But we would like to keep these appointments a little bit self-standing. So I do a smooth introduction to the overall idea and infrastructure before giving the word back to Joe that will guide you through the actual hands-on tutorial. So basically, the aim of this brief introduction is to make you understand this Euler diagram that probably to most of you will be a bit cryptic at the moment. But I will come back at the end to, and I guess you will have understood what it means. So let me start from the basic motivation of the whole FAIRmat activity. Most of you are aware that at some point the scientific community became aware that we need so-called FAIR data, where the very catchy acronym FAIR stands for Findable, Accessible, Interoperable, and Reusable Data. According to some, they are also maybe repurposable or recyclable data. And very, very short, all this has to do with annotating the data. And where annotation comes in is about metadata. So the data should be findable. That means that the metadata that annotate the data should be unique, should be accessible. The meta and the metadata should be accessed somewhere. And then a bit of a higher level request is that the data and the metadata are interoperable, and this is where the concept of ontology comes in. Essentially today I will not talk about ontology, but this is what lurks behind the interoperability request of the data. And then the idea that the data should be reused in some sense or for different purposes that the one that they were initially produced for. And this calls for the concept of provenance, that is basically tracing all the history of any piece of data, where it came from. So I used many times the word metadata already, and both of us have the intuitive understanding of what metadata is, but I would like to spend a few words on more technical level what metadata means from a perspective of data science. So first of all, one has to keep in mind the concept of data object. In some contexts, is also called information resource. That can be visualized as a row in a data table. So imagine that you have data simply stored in tables. Any row in this data table could be a data object, and here it would be like a minimal data object in computational material science, where you have some atomistic structure, some method that was used for doing a certain calculation, and some observable that was calculated. Now, once one has identified a data object, one has to recognize that the columns of this data object are called attributes of the data objects. Now, as simple as that, these columns, these attributes, are data or metadata, and depending on the context, they are data or metadata. Let me try to explain what I mean by context. So here I already added also a new column that is, say, a new structure, because maybe one has done a calculation of some structure, and then as an outcome of this calculation, a new structure has been produced because one has calculated forces and it has modified the structure according to the forces. And so let's say that what has been calculated could be called the data, and everything that identifies, explains the data on this side with red. Sorry for the color blind. These three columns are red and these two are green. So data are green and metadata are red. Probably next time we'll change these colors. And so depending on the content, this could be a data or metadata, because, for example, this new structure could become the metadata to a new calculation, to a new data object, and so on and so forth. So exactly the same item could be data or metadata depending on the context. Now, we also have more commonly understood as metadata attributes, such as access privileges, who can access when the data were uploaded, and this kind of information. We call this administrative metadata. And then we have, as I mentioned before, the provenance. So how a certain data object, or essentially the data in a data object, was derived in a wider sense. So an attempt of a complete definition of metadata would be the attributes that are necessary to locate, fully characterize, and ultimately reproduce other attributes that are identified as data. The metadata include a clear and unambiguous description of the data and their full provenance. So as you see, we stress the point of context, so attributes that are identified as data. So depending on the context, something is data, something is metadata. And we stress also the idea of reproducibility, that is the main motivation of all this enterprise of FAIR data, to really make science reproducible. Following these ideas, or actually preceding this, for the idea were actually published, the NOMAD laboratory was established. The NOMAD laboratory is an infrastructure that was established at the end of 2014 that aims at storing and managing FAIR data for material science. The structure of the laboratory from the beginning was such that we wanted to have a storage of atomistic simulation data as they were, meaning that people do calculations with some codes using the community, or could be also kind of handmade, meaning some code that is not really widely shared, but it could be used in a group, in a specific group. And this has input and produces some outputs. And the idea is that in the repository of our infrastructure, we have the data as they were used and came from the calculations themselves. And then we have a processing part that maps the input and the output, at least part of it, into our metadata infrastructure that I will briefly introduce in the next few slides. And then we have access modes to this infrastructure that are a kind of browser. Joe will amply use this browser to show you how one access the data, and then we have a kind of in some sense, advanced access to the data, and that allows for in-depth analysis of the data, including some artificial intelligence tools. And Joe will also show a little bit of this in the third tutorial today. Okay, so now that I have mentioned these access kind of channels, I can also say that as a mnemonic, one way also to remind the AIR part of FAIR is also artificial intelligence ready, meaning that at the end of the day, one of the most interesting usage of the data that are stored in the NOMAD repository, but in other FAIR repositories, of course, is that one can use a big amount of data for artificial intelligence analysis. Okay, so far I talked about the NOMAD laboratory that was established in 2014. And so it was initially created by Matthias Schäfer and Claudia Draxel. It has built in a fairly small amount of time a huge amount of calculation. Also, thanks to the kind of donation of some of big US databases that you see here mentioned. And so we have data from many different codes that are used in the community. Now it is the time to introduce a wider enterprise that is FAIRmat. It was established at the end of 2021. This is funded by the German infrastructure for research data, an FDI. It is chaired by Claudia Draxel and deputy is Christoph Koch. So FAIRmat can be understood as a superset of the NOMAD laboratory, and has many different branches. So while the NOMAD laboratory initially was focused on the computational data, now FAIRmat has a full area that is dedicated to synthesis. Here I mentioned, so the code here is that we have the PIs of each area and the coordinator indicated here, and then we will go through the areas. So we have an area dedicated to synthesis data with a few tasks, so with the different synthesis routes. We have an area dedicated to experiments with initially identified 5 different experimental techniques to be verified, so whose data would be being verified. And then we have the computational part, and here I put again the NOMAD logo because essentially this ab initio calculation part and to some extent the classical simulation part is built on the original NOMAD laboratory, and then we have also now expanded to excitation. We have a full area dedicated to the infrastructure. Here you see more people because we have 2 PIs, a coordinator of the area, but also an overall coordinator of the infrastructure, because clearly the infrastructure is something that talks to all the other areas. And so we have essentially the architect of the whole infrastructure that supervises the whole implementation, and we have different subtasks also here in this implementation infrastructure area. But of course, we want also to show that these activities are useful in the community, and so we have a full area dedicated to use cases. Even though the logo is just a battery, we have many more than batteries here. Yeah, so each of these tasks ideally will showcase how one can use a FAIR infrastructure, the FAIRmat infrastructure, to store, manage the data, and possibly also document artificial intelligence analysis of this data. Essentially, related to what is happening today, we have a full area dedicated to the communication with the community. Training schools, this is what we are doing today. Okay, so the coordination, I don't have a specific slide. Of course, we have a full administrative area because the enterprise is quite big. Now I want to give the flavor a little bit of how we intend the mapping into metadata of computational material science data. So I changed the color of the logo because now I am focused on the computational part of FAIRmat. So the idea is that if we have an atomistic simulation code, at some point in the future we will go beyond atomistic simulations, but in computational area, but for the moment we are kind of mainly focused on atomistic simulations codes. Of course, a code has a name, a version, some library that we will use for compiling it, and this should be part of the metadata that we provide. And then typically, if we do a calculation, we have some input structure, coordinates, information on the cell vectors, and if we are doing a force field calculation, we may also give the bond topology of the structure. And then we have some physical model, or overall input model. There's some physical model, so exchange correlation treatment, relativistic treatment, for example, but also the numerical implementation, basis set and numerical integration settings that should be recorded in order to kind of tell observables that one may be interested in, say total energy forces, where they came from. So all this information here is explaining where the data, the output is coming from. Of course, one can have extended output, so same calculation could have a lot of interesting outputs to be analyzed. And also the input model could be complicated, right? I mean, it could be that one does self-consistent calculation and then does a perturbation on top of the self-consistent calculation. It could be that one is space partitioning in the physical model itself, so QMMM kind of things. And this should be also properly annotated. So in practice, this kind of complex hierarchical structure is boiled down to different tables that contain the different, so the semantically different part of the metadata that are connected to the data that is the output of the calculation. And our metadata schema in the computational part maps directly this kind of semantical partitioning of the information. So we have things that we call sections in the metadata, and we have something about the system, something about the method, and something about the results, and something about the overall specification of the calculation. At this point, metadata and data get a little bit blurred in what is data, what is metadata, right? So we have everything that is indexed properly in our metadata scheme. So the basic of this schema was introduced a few years ago. Now it is more complex, let's say, but the basic idea is still here, represented in this slide. As Joe will show thoroughly, we have a way to browse this complex metadata schema, and here I just reported. So if you go to this link here, you will find it, but don't try to rush now because you will be guided later there. So this is a snapshot from the web page in which we have this run section that contains, you see, method, system, and calculation sections. Something more, but stay focused on what I point at. And let's say in the section system, you will have, for example, information about the atoms, that could be how many they are, and everything that you may imagine is useful to be annotated about the atoms to which the calculation is performed. Why? I see my screen sharing is paused. Is it true? Are you seeing?
Say that again.
I have a warning that my screen sharing is paused. Do you see a slide with the meta info?
Yeah, it's highlighted on run.
And now you see back the.
No, it's still the same one.
Okay, interesting. Resume share. Probably I hit the button.
Okay, there you go.
Okay, hopefully I realize immediately. Good. So now I want just to show one direction in which the metadata schema gets more complicated. So this was the same slide I showed before, in which we have the input model. Sorry, the simple mode in which we capture a somewhat simple calculation. And then we can say, okay, we can also chain calculation, or in any say combine calculation in such a way that we have an overall input. Then the calculation produces some output that serves as an input to another calculation. So some observable and some structure becomes the input to another calculation. Then we could have metadata for the overall set of calculations. Say we are doing some force relaxation, some molecular dynamics, and so on. So we have information of the overall set of calculation that I will start calling workflow. Yeah, for example, if it is about molecular dynamics, it has its own specific metadata. And then we have an overall output. Say that if we are doing some molecular dynamics, we may be interested in some average of some quantities or correlation functions and so on. But the key idea here is that we would like to store calculations that are, say, workflows that could be complex at will in such a way that we access the data, the observable that were measured for the overall workflow. We know what was the setting for the overall workflow, but we may want to access calculations that are inside this workflow at the same with the same level of detail that we have for the overall workflow. So if we are doing, say, geometry optimization, yes, we are interested in the relaxed structure, but maybe we are interested in all the structures along the geometry optimization because they could be useful for some machine learning potential learning. So the aim here is to index the data properly such that we can access all level of hierarchy in a workflow. And this is where Joe will be showing recent results, let's say, in the implementation, so that hopefully you will be inspired to contribute with data and also give us feedback on this. So hopefully at this point, this Euler diagram becomes more clear. We have a FAIRmat, that is the overall consortium that develops in different directions. Part of FAIRmat is the NOMAD laboratory. That is the infrastructure that can be used to store and analyze the data. A subset of this infrastructure is the Turing computation area that we will be focusing today. Actually, today we will be focusing on molecular dynamics, part of Turing computation. And then I put workflows intersecting the different subsets, because today you will see essentially workflows for molecular dynamics, but this is an overall enterprise encompassing whole Turing computation, but also the whole NOMAD infrastructure. To close, is what we are doing or what we have already achieved with FAIR? I think so, especially the data are findable because we have unique names and human readable descriptions in the metadata. The data are accessible. Each data object has a unique URL. And they can be accessed via an API, as you will see. The data are to some extent interoperable. At least we achieve the fact that we go beyond the specific code that has been used to produce the data. The schema is extensible, even though, of course, by making a schema extensible, we have challenges because we may have redundant or conflicting metadata. This should be at some point resolved. And the data are reusable via, so we map the provenance of the data, and as you will see, we can do data analytics on the fly on the data that are retrieved, more or less on the fly, on the data that are retrieved from the archive. Okay, with this I essentially close, giving so I will leave a little bit space for questions, but essentially Joe will then go through the 3 tutorials that we have prepared today. But before that, I want to thank the main people behind the workshop today. So Lauren and Alvin have contributed in the implementation of the graphical interface and the workflow visualization that you will see today. Adam has curated the notebooks that you will use. Lucia has essentially organized the event. And so Shema and Nathan are also online helping with questions and so on. They are also in the area C, as Joe and myself. They will have more dedicated tutorials to their specific subject, but today they are helping us online. So I stop here.